Alright, for today's lesson, we go on to a new chapter that has been newly added to your syllabus, which is Astronomy and Cosmology. Astronomy and Cosmology is a branch of science that deals with a study of objects out in space, outside of Earth's atmosphere. In our syllabus specifically, we are more interested with stars. Now, what are stars actually? Stars are massive celestial bodies that emit large amounts of heat in addition to light and other electromagnetic radiation. When it comes to stars, there are a few properties about the star that we're interested in. The first one being the luminosity L of the star, which is actually the total power of radiation emitted by the star. Since it's actually the total power, the unit of luminosity would be in watts. And if you imagine right now that this is your star, as light is being emitted, heat is being emitted, or other forms of EM radiation are being emitted, they are actually emitted out in all directions, like this. So if they are emitted out in all directions like this, when you look at it in a 3D view, they are actually emitted out in the form of a sphere, which gets bigger and bigger with time. So as light leaves the surface of a star, it tends to spread out uniformly in all directions in a sphere where the surface area of this sphere is actually equals to 4 pi r squared. So here, the surface area of the sphere where the power has spread to is going to be 4 pi r squared. And given time, that sphere is going to get bigger and bigger. The power will be spread out even larger over a certain area. So given time, this sphere will only get bigger and your power will be spread out significantly over a larger area. After spreading out significantly, if you were to try and measure the power, what is measured will only be a fraction of the luminosity. Now, when you try to measure the power emitted by the star, there's another quantity that you would use, which is actually your radiant flux intensity F. So be careful about the symbol that is attached to radiant flux intensity. Previously, we always associate the symbol F with force, but in this chapter, F here actually refers to the radiant flux intensity. Please do not mistake it as force. So radiant flux intensity here is actually defined as the power transmitted per unit area by a star that is measured on the Earth. Okay. Now, since radiant flux intensity is the power transmitted per unit area, this would mean that the unit of radiant flux intensity is actually going to be watts per meter squared, following the units of intensity that you've learned in waves as well as quantum physics. Okay, radiant flux intensity is actually intensity itself, just that it's been given a different name for this chapter. Okay, so when you think about luminosity and radiant flux intensity, well, when you want to make a comparison between the two quantities, luminosity refers to the total radiation power that leaves a star, while radiant flux intensity is the power per unit area or intensity received at a distance from the star, which is usually on Earth. Let's consider that you want to measure the radiant flux intensity on the Earth. Before you can go about in doing that, there's one assumption that you first need to make. That one being that the radius r of the sphere where the power is spread out to is the distance d between the star and the Earth. If you look at the diagram that has been drawn, the radius of your sphere is actually this one. But at the same time, it is also the distance d between the star and the Earth. So r will be equals to d. So the surface area of the sphere, in addition to it being 4 pi r squared, you could have rewritten it as A equals to 4 pi d squared. So right now, as the power keeps spreading out from the star, by the time the radiation reaches the Earth, it has been spread over an area of 4 pi d squared, from which you can now calculate the radiant flux intensity. Now, from the basic definition of radiant flux intensity, which was power per unit area, power here for a star is luminosity, and the area A here to which your power was spread out to was actually the area of your sphere, which is 4 pi d squared. So your radiant flux intensity can thus be written as F equals to L over 4 pi d squared, which is what you're seeing right over here. Now, the equation assumes that power from the star is radiated uniformly through space and no radiation is absorbed between the star and the Earth. If you have any given star, the luminosity here will be constant. Thus, radiant flux intensity is inversely proportional to your distance squared. This is known as your inverse square law. So to get a better idea of what we mean by that, if you refer back to the equation here, if L is constant for a given star, L is constant, and not to mention 4 pi is also constant, you will get that F is inversely proportional to D squared. This is actually your inverse square law of flux. Okay, so why is this so important? You have to look at the next page. The inverse square law actually tells us that if your distance were to increase by 2 times, your radiant flux intensity would decrease by 4 times. Whereas if the distance was increased by 3 times, your radiant flux intensity will be decreased by 9 times. Okay. Now, another way to understand why this happens is to look at how the area changes with distance. If you consider that this is your star and power is radiated outwards in the form of a sphere, let's just consider a particular section of area A over here that is at a distance of r from the star and having an initial intensity of I. So right now, if you try to relate the area to distance, area is actually 4 pi d squared. If 4 pi is a constant here, this will have told you that area is directly proportional to your distance squared. And then from here, you can actually make some sort of relation out of it, where if distance d increases by 2 times, area increases by 4 times, whereas when distance increases by 3 times, area increases by 9 times. So right now, let's consider this. At distance d equals to r, if your distance were to increase by 2 times, your area would have been spread out to 4 times as large compared to the original area. So if this is area A, it would have been spread out to 4 times the original area. So right now, when you look at the intensity that was originally emitted, that intensity is now spread over 4 times the area. It will be divided by 4 times. So that's why here your intensity reduces by 4 times. That is what you're seeing right over here. When distance increases by 2 times, your radiant flux intensity decreases by 4 times. Then how about if you were to increase your distance by 3 times? From d equals to r, you go to d equals to 3r. This is where distance is increased by 3 times. So based on the relation that you have over here, when your distance is increased by 3 times, your area would have been spread out to 9 times as large. So right now, if this is area A, you now have 9 times the area A. And now, if you look at the original intensity I that you had from before, it is now being spread over 9 times the area. The intensity would be reduced by 9 times. So your intensity is I over 9. That's what you're seeing right over here. Your distance increased by 3 times, your radiant flux intensity decreases by 9 times. Now, this also explains why stars further away appear fainter, because the emitted light is actually spread over a greater area. The intensity that you see is less, the intensity received is less. And lastly, the significance of the inverse square law of flux is that it will tell you that if you measure a larger radiant flux intensity from a star, the star will actually be closer to the Earth. Because if you look at the relation, radiant flux intensity being inversely proportional to distance squared, if your radiant flux intensity measure is larger, your distance is actually smaller. The star is actually closer to your point of measurement. Okay? Now for the next part, we move on to standard candles and stellar distances. Now, if you want to measure the distance between the Earth and a star, measuring those astronomical distances accurately is an extremely difficult task because direct distance measurement is simply not possible. So we would have to rely on indirect methods instead, where standard candles now come in useful. A standard candle is an astronomical object which has a known luminosity due to a characteristic quality possessed by that class of object. Common examples of standard candles will be your Cepheid variable stars and your type 1 supernova. Cepheid variable stars are a type of pulsating star which increases and decreases in brightness over a set time period. Now, when you see pulsating here, pulsating star, it actually means that the star is twinkling or blinking. In other words, okay, the brightness will increase or decrease with time, okay, and from there, scientists found that the variation in its brightness has a well-defined relationship to the luminosity. That was what allowed them to know the luminosity of a Cepheid variable star. As for the second example, your standard candle, which is your type 1a supernova, a supernova is a star that undergoes a massive explosion at the end of its life cycle. So the power, or rather the luminosity produced at the time of explosion for a supernova is always the same. If the luminosity of a source like a standard candle is known, then its distance can be estimated by measuring the radiant flux intensity of the electromagnetic radiation arriving at Earth, and then subsequently using the inverse square law of flux. So recall the equation that we've learned before this, where radiant flux intensity is luminosity divided by 4 pi d square. If you're able to measure the radiant flux intensity, this one is measured, and then you know the value of the luminosity, this is known, then it follows that your distance d can be found. Okay? If the radiant flux intensity equation from before allows us to find the distance to a star, the next thing we want to know is the temperature of the star. For this, we will need to make use of Wien's displacement law. First, we need to define what is a black body. A black body is an object which absorbs all radiation that falls on it and is a good emitter. It does not reflect or transmit any radiation. So meaning to say right now, if this is your black body, any radiation that falls on it will be completely absorbed. It's not supposed to do any kind of reflection, meaning to say if the radiation comes here like this, it's not supposed to be reflected the other way. So reflection is not something that is supposed to do. And then also, it's not supposed to transmit any radiation, meaning to say if your radiation comes in here like this, it's not supposed to let the radiation pass through it so that it leaves the other end. So here, transmission of your radiation is also not something that your black body is supposed to do. It's only supposed to completely absorb all radiation on it. So right now, stars are the best approximation to a black body. When it comes to a black body, the radiation emitted from a black body has a characteristic spectrum that is determined by the temperature alone. So right now, if you're talking about a graph of intensity versus wavelength, your graph should have a characteristic shape like this. This is what we meant by your characteristic spectrum. Okay, there will be variations in your wavelength as well as your intensity that varies according to this particular graph shape. So think about it. If your black body is your star, the star is continuously emitting out all forms of radiation. So the radiation could be your X-ray, it could be your gamma ray, it could be your UV, it could be your visible light, it could be your infrared, and many other wave types. So it follows then that you should have various other wavelengths because you have different wave types being emitted, and at the same time you also have different amounts of it being emitted. So hence this explains to you why you have different intensities. So if you were then to plot a graph of intensity versus wavelength for 4 different stars as shown below, they would still show you the same characteristic spectrum, just that they differ only by their temperature, specifically the thermodynamic surface temperature. So right now at 3000 Kelvin, you have this shape over here. And then at 4000 Kelvin, you have this shape over here. And at 5000 Kelvin, you have this shape over here. And lastly, at 6000 Kelvin, you have this shape over here. Now, of interest to you are the peaks that are indicated right over here. There is a relation between the wavelength and the temperature that you could actually see. If you're talking about 3000 Kelvin, this is the wavelength. At 4000 Kelvin, this is the wavelength. And then at 5000 Kelvin, this is the wavelength. And then lastly, at 6000 Kelvin, this is the wavelength. You can see that as temperature increases, the wavelength at peak intensity actually decreases. This is where Wien's displacement law is defined, which states that the wavelength at peak intensity or maximum intensity is inversely proportional to the thermodynamic temperature. Now, when you look at the lambda max, it's easy to misunderstand it as the maximum value of your wavelength. That is actually not the case here. Lambda max refers to the wavelength that you have at peak intensity or maximum intensity. The wavelength value itself there is not at the maximum, okay? The maximum here actually refers to the point where you have peak intensity or maximum intensity. Now, for Wien's displacement law, if you want to write it in the form of an equation, it will be lambda max inversely proportional to T. If you then want to get rid of the proportionality sign that you see here, what you need to do is that you will have to introduce a constant where lambda max is equals to B over T. Let's assume that the B here is actually your constant. So from there, you will get lambda max times T equals to B. That value of B that you see here is actually 2.9 times 10 power minus 3. Now, you don't need to remember the value of the constant. If your question requires you to make use of it, you will be given inside the question itself. Okay? From Wien's displacement law, lambda max is inversely proportional to temperature. The equation tells us that the higher the temperature of your star, the shorter the wavelength at peak intensity. Not only that, it will also allow us to guess out the color of the star. To do that, you will need to refer back to the visible light spectrum, Roy, G, Beef, red, orange, yellow, green, blue, indigo, and violet. If you're going towards the right side of your spectrum, your wavelength is decreasing. On the other hand, if you're going towards the left side of your spectrum, your wavelength is increasing. We know that lambda max is inversely proportional to the temperature. If your temperature is high, your wavelength would be decreasing. This would mean that you're going towards the right side of the spectrum, you are actually going towards the bluish side of the spectrum itself. And then on the other hand, if your temperature is low, your wavelength is going to increase. So you're actually going towards the left side of the spectrum, you're going towards the reddish side of your spectrum. From here, we can then conclude that the hotter your star, your wavelength is actually decreasing, so you're going towards the bluish side of the spectrum, your star tends to be white or blue. But on the other hand, if your star is cool, your temperature is low, your wavelength is high, you're going towards the reddish side of your spectrum, so your star tends to be red or yellow. That's how you work out the color here, by looking at how the wavelength is changing. And now for one last part before we move on to your past year question examples, let's look at Stefan-Boltzmann Law and stellar radii. Now, when you're talking about the luminosity of a star, it depends on its surface temperature and radius, which is related together by the Stefan-Boltzmann Law. The law states that the total energy emitted by a black body per unit area per second is proportional to the fourth power of the absolute temperature of the body. If you look at the definition closer, total energy per unit area per second sounds kind of familiar, isn't it? It's actually relating to your intensity. It is power over area, but if you were to expand it out, it's actually energy over time over area. So you can actually think of Stefan-Boltzmann law as saying that intensity is proportional to the fourth power of its absolute temperature, meaning to say right now, intensity is proportional to T raised to the power of 4. If you want to write it out in an equation form, the full form of the equation is actually L equals to 4 pi sigma r squared T power 4. L is the luminosity, R is the radius of the star, which is also known as your stellar radius. Sigma is a constant called the Stefan-Boltzmann constant. The value can be obtained from your datasheet in your exam paper. And then the last one here is T. It is the surface temperature of the star in Kelvin. So how do you get this equation in the first place? While the derivation is not required in your syllabus, it's a good idea to know how it's derived in order to deepen your understanding. So right now, let's just say that intensity is directly proportional to the temperature raised to the power of 4. You want to get rid of the proportionality sign here, so you need to introduce a constant. That constant is your Stefan-Boltzmann constant, sigma. So from here, you then try to substitute out your intensity here. Okay, so intensity, as I mentioned earlier, is actually your radiant flux intensity. So radiant flux intensity is L over 4 pi d squared. And then from here, right now, there's one other thing to note. When you're talking about the temperature T here, is the surface temperature of the star. So since this T is the surface temperature, the D, or rather the distance you're considering, is really just the radius of the star itself. So D is equals to R here. Therefore, your I is L over 4 pi R squared, which you then want to substitute inside here. So now you get L over 4 pi R squared equals to sigma T power 4. And then if you try to simplify it, making L the subject, you get L equals to 4 pi sigma R squared T power 4. That's how you got the Stefan-Boltzmann equation here. Okay. Now, when you do your questions later on, you will notice that you will have to use a combination of Wien's displacement law and Stefan-Boltzmann law before you can find the radius of a star or the stellar radius. Let's recap some of the equations that we've learned so far. The first equation is radiant flux intensity equals to luminosity divided by 4 pi d squared. You would use this equation to find the distance to the star. You're finding what is d right over here. And then for the second equation, it's actually Wien's displacement law, where you say that lambda max is inversely proportional to your temperature. This is Wien's displacement law. You use this equation in order to find the surface temperature of the star. You're finding what is T right over here. And then for the last equation that you've learned is luminosity equals to 4 pi sigma R squared T power 4. This is your Stefan-Boltzmann law. Okay. Now you would then use this equation in order to find the radius of your star. Okay, so all these equations that you've seen here is actually meant to find something about the star. The first one was to find the distance to the star. The second one was to find the surface temperature of the star. And then the last one is to find the radius of the star itself. Okay,